Right. So let's look at steel columns. Steel columns. Right. So when it comes to steel columns, it can be a compound column. Compound meaning that this is made out of different pieces to make one structural unit, or it can be a hot rolled section, hot rolled standard section. Right. So that's what you can have when it comes to steel columns. So what's a column? A column is a vertical member. Right, which is loaded along its axis, meaning it's a member like this, and we are applying a load there, let's say a load P, right? So because we are applying a load P like that, this member will then transfer that load to whatever support which we have there, right? So it is very much similar to, in fact, it is a strut, right? So it is a compression member. So columns are compression members. So that procedure which we followed when we're designing compression members is more or less the same as what we do when we're designing hot rolled standard columns, right? So I've just given you an example on how to do hot rolled standard columns. If you look at the link which I sent on your WhatsApp group, it's dealing with having a hollow section, rectangular hollow section like this, and this rectangular hollow section which we are having, that rectangular hollow section which you are having, they want you to calculate the maximum load which that column can carry. They will give you the length, then the effective length of that you would have to determine, and all that. So I've demonstrated how that is carried out in that video. So this time around I want to put my focus on what they refer to as compound columns, right? So once I'm done with compound columns, then we will come and do an example on hot rolled standard sections, but an example in which we are comparing maybe 3 or 4 different sizes to see which one would be the optimum size to use for a particular situation. So that's what I want to do. Right, so let's look at work example 2.1.6 on page 72 of your textbook, which reads, calculate the maximum axial load this column can support if the column is effectively held in position at both ends but is not restrained against rotation. The actual height of the column is 3.5 meters. So this one is example 2.16. Right, so this is example 2.16 in your textbook. So that example 2.16 in your textbook, it requires you to calculate maximum load which can be carried by a column, right? So its length is how much? 3.5 meters. 3.5 meters. Then the conditions are also given. That is the conditions relating to how, right? So let's look at this question. Right? So we are having a column, right? But the cross-sectional area of this column is what you see there. So in essence, it's something like this. And I said, so we are loading, we are applying a load here, P. That's what we want to determine. And that value is something which is unknown at the moment, right? So we want to find out what is the maximum load which this kind of column can carry, right? So this kind of column is not a standard column. It's what we call a compound or a built-up. So what it simply means is we can make use of welding to join these components to form that column, right? Right. So let's look at the conditions, right? We can be told that the column is effectively held in position at both ends, but not restrained against rotation. Right. So it's effectively held in position at both ends, but it is not restrained against rotation. So this statement is important because it's a statement which we can use, which we're going to use when it comes to designing our values, right? So let's now look at how do we proceed here. So the first thing which we have to do is to determine the moment of inertia, right? So determine moment of inertia about the weaker axis, right? So why am I putting emphasis on the weaker axis here? I'm putting emphasis on the weaker axis because that is the side where it is going to buckle. Remember, if you have a column and you apply a load on that column, it will have a tendency to bulge outwards. It will have a tendency to bend like that. And that bending is what we refer to as buckling, right? So to prevent buckling, we need to make sure that we provide a section size which is able to resist this buckling, right? So the buckling will always occur about an axis which is weaker, right? So if you look at IXX and IYY, right? If you're dealing with something which is doubly symmetric, right? You always notice that one of these two values is greater than the other. One value is greater than the other. So the smaller value then becomes the weaker axis. So by inspection, how do you notice that this side is weaker, right? So you only look at the overall dimensions. If you look at the overall dimensions, they will tell you which side is weaker. So this is the x-axis, and this will be the y-axis, yy, there. Right, so if you look at the dimensions which I've just given you, what did we say is the overall depth? We said it's 270. It is 270, and we said the overall width is 180. Right. So by just comparing these two values, right, this one and this one, it tells you that this IYY is the weaker side. Why is it weaker? It is weaker because its height here from there to there is smaller than the value which we are getting here from there to there. So it tells you that this one is going to be the weaker axis, right? So if you are determining the weaker axis, it means we are rotating this section. Means we are rotating this section like this, and we want to calculate the second moment of area. So this is y, and we know that from there to there, this is going to be 180. From there to there, this is going to be this is going to be a value of how much? What was the thickness? 12 millimeters. Okay, 12 millimeters. Then from there to there, this value is going to be 270. Right. Now, the second moment of area of an H section like what you see there, right? You don't need to waste time, because remember, in your test or in your final examination, they want you to calculate this thing. And you notice that in your textbook, they start by calculating IXX, then later on go to calculate IYY, then later on use IYY as the basis for further calculations, right? So because you know that this weaker axis is going to be the one which you're going to use, there is no need in you wasting time calculating IXX, because it's not going to be used there in any case, right? So in order for me to get IYY, this is going to be equal to the sum of I neutral axis. So that's the shortcut which you should know. If you are given this type of section, like the one which I'm showing you here. So IYY is going to be the sum of I neutral axis. All right. So what is I neutral axis? I neutral axis. I neutral axis for a rectangle, right, is BD cubed over 12. You remember we used this formula yesterday. So we're going to apply it again. So what are we going to do with this? We're going to apply this formula for that rectangle and that rectangle and that rectangle. Right. So this is going to be equal to 2 multiplied by BD cubed over 12 plus B1 D1 cubed over 12. So why am I saying BD cubed over 12? From there to there, that is B, and this value is my D. And because this shape is identical to that shape, that's why I'm multiplying by 2. And B1 D1, I'm now referring to the distance here between the two sections here. So if that is an overall of 270, and we have 12 millimeter thickness on flanges, what will be this distance? We already know that the thickness here is 9 millimeters. So what is going to be the distance between the flanges from there to there?
So I get 246.
Huh?
246.
246 millimeters. Right. Right, so this 246 millimeters is the distance between that, and that's what we're going to be using as B1. D1 is going to be the thickness. So substituting values, this is going to be equal to 2 times B, and the value of B is 12, multiplied by D cubed, which is 180 cubed divided by 12, plus 246 multiplied by D cubed, which is 9 to the power 3 divided by 12. What answer do we get from that calculation?
So, do you want it in megapascals?
Matthew, not everything is measured in megapascals.
Okay.
Not everything is measured in megapascals.
Yeah. Millimeters.
Is measured in millimeters to the power 4.
Oh,
Right. So because our values are in millimeters already, what I just want you to do is just give me a figure and maybe raise it to 10 to the power 6. Express it as 10 to the power 6.
so then it's 1.959.
1.595
959.
959.
Yeah.
959 times 10 to the power 6 millimeters to the power 4. Is that the correct value?
Yes, sir.
Okay. So once you get this, then we are good to go. The next thing is determine area of cross section, which is area. So the area of cross section is equal to the sum of areas, small letter areas. So if you look at the area of that section plus the area of the web plus the area of this other flange will give you the total area which we want. So this is going to be 2 times 12 times 180, 2 times 12 times 180 plus 246 multiplied by 9. What answer do we get?
$6,534.
6,534 square millimeters. Right, so that's the area. Then from there, you want to determine what is called the radius of gyration. So determine the radius of gyration. Determine the radius of gyration. So the radius of gyration, let's say about the weaker axis, about the weaker axis, and the radius of gyration is given by small letter r, right, or small letter I, because in your red book it's given a small letter I, but for other calculations you can use small letter r. So this is going to be R about the y-axis, RYY. So RYY will be equal to the square root of IYY divided by area. So the area is under the square root sign. So this then means that we are going to have a square root of 1.959 times 10 to the power 6 divided by an area of 6534 and everything under the root sign. So your radius of gyration, you'll get it in millimeters. If you do it this way, we're going to get it in millimeters. So what answer do we get?
So I got 299.816.
Square after the square root.
Oh wait, let me put the square root.
So it's 17.315.
17.315 millimeters. Right, so that's the radius of gyration. So once we have determined the radius of gyration, the next thing is we need to determine the effective length of the column. So determine effective length of the column. And the effective length of the column is LE, right? But how do we determine the effective length of the column? The effective length of the column, we determine it using a table which is on page, let me just go to the table. We get it from table 19, so the reference is table 19, and right. Now, so if you go to table 19, do you have your textbooks on page 100? Please go to page 100. Are you there on page 100?
Yes, sir.
Right, so if you go to page 100, you notice that there is table 19 which talks about the effective length of struts with standard end conditions of end restraint. So if you look at column 1 has a condition of end restraint, column 2 has got effective length, then column 3 has got a sketch which describes each condition of end restraint. So we are told that it is effectively held in position and restrained against rotation at both ends. Then our condition now is as follows. Our condition is the column is effectively held in position at both ends but not restrained against rotation. So we are looking for that condition. Effectively held in position at both ends but not restrained against rotation. So if you look at that condition, it is the third condition. And if you then go to column number 2, in order to calculate the effective length, we multiply 1 by L, right? So that's why we needed to understand that. So L is equal to 1.0 multiplied by the actual length of the column, right? So because of that condition, it therefore means that our effective length is equal to 1 multiplied by, what was the length of that column? The length of that column is 4.65 meters. So here we're going to multiply by 4.65 meters, which is equal to 4.65 meters. Right? So that's the effective length. So if you look at the type of support there, we are having pin supports at both ends. So once you are done with that, you then need to determine the slenderness ratio. So determine the slenderness ratio of the column. Determine slenderness ratio of the column. But so when it comes to the slenderness ratio is equal to the effective length divided by radius of gyration about the weakest axis. So slenderness ratio is a dimensionless number which gives us the ease with which a column buckles. The larger the value, the easier it is for a column to buckle, right? The smaller it is, then the more difficult it is for a column to buckle, right? So this slenderness ratio, you have to convert the units of measurement to be the same. So our effective length was given as 4.65. I'm converting it to millimeters, which is 4,650 millimeters, divided by a radius of gyration of 17.315 millimeters. 17.315 millimeters. So that's in millimeters, this is in millimeters. So the final answer is dimensionless. What do we get? 4650 divided by 17.315.
So I get 268.55.
Yay, 268. 268 point what?
553.
553. Call it 269. These values you can round them up, no problem. You're going to see why that is the case. So once you have determined the slenderness ratio, you can then go and determine the maximum allowable compressive stress. Determine maximum allowable compressive stress. Right. So we get this from table 17. But remember, we are referring to SA BS0162 part 3. So table 17, right? That's the reference. Table 17, that's the one which we're going to use. So let's go to table 17, and table 17 is on page right. So the clause which governs this is clause 8.1.1. Right. So the table 17, you are going to see that it's got a slenderness ratio. So it's got a slenderness ratio on column 1, 2, 3, 4, and on the first row you're going to see that we've got 0, and it goes to +1, +2, +3, +4, all the way to +9. Then when we go downwards, we have a slenderness ratio of 0, 10, 20, 30, 40, 50, and it goes all the way until you get to a maximum slenderness ratio of 350, right? So for slenderness ratio is equal to 269. So the compressive stress, which is given as PC, is equal to how much? So that's what we want to look at. We have used table 17 before, right? When we're designing struts. Guys, when we did design of compression members, when we're doing design of plane frames, didn't we use table 17?
Yes, sir, we did.
We did. So we know
We did, sir.
so we know how to use table 17, right? Right. So let's go to 200. So if you go in column 1, 230 is the last number. We want to go to 260. So if I go to 260, if I go to 250 there, this is going to be 250. Then from 250, 59, then it goes all the way to 300. So what we need to do is we don't really have a value tabulated for 260. So for 260, we're going to need to do a linear interpolation. Right? Sorry, for 269, we're going to do a linear interpolation. So it's a value which is going to be somewhere between 15 and 11, right? Because we've got a value of 250, and for 250 we have a value of 15 megapascals. Then for 300 we've got a value of how much? 11 megapascals. All right, 11 megapascals. So what do we do for 269? For 269, then we can do linear interpolation. So what we can do is we want to find the value of PC for a slenderness ratio of 269. Guys, are you sure that the slenderness ratio which you gave me is correct? Let's go back. Something is not making sense here. Something is not making sense here. Guys, this value, I'm doubting it. Do like this: 1.959 times 10 to the power 6 divided by 6,534 to the power 1 over 2. What do we get? I'm doubting this value. Looks like that value is too small. That's why that slenderness ratio is just too large. Redo that calculation, please.
It's correct, sir. It's 17.315.
You said 17 point what?
315.
No, man. What are those dimensions? I just want to compare. What am I doing here? I just want to compare those values with what I'm having here. What is our overall depth? 270. What is our overall depth? Talk to me.
Yes, sir, 270.
It's 270, right? And what is the width of that thing? 180.
Yes, sir.
And
So is the length of the column correct? 4.65, is that correct?
no, the length of the column is correct, but what I'm now doubting from you guys is this value of 1.959 times 10 to the power 6. That's what I'm now doubting, because you know what, I'm looking at the dimensions of a standard I section here, and this standard I section which I'm talking about is a 203 by 133. And if you compare the dimensions of a 203 by 133, right, its dimensions are smaller than what we have here, and the second moment and the radius of gyration of that standard section is 31. About IYY, it is 31.
So, I had a problem with the first calculation. It's just that you were moving too fast and I had network problems. I think that's where the problem might be.
The first calculation, this one?
No, yes. It's supposed to be, I get 79744 if you, yes, that one.
This one, right?
Yes.
Yeah, there's a problem with this figure.
It's just that you're moving too fast, so I was like, "Ish, maybe I'm doing something," but that's the one I'm seeing wrong. It's 79744.5.
So I get 11.679 if I do that.
Yeah?
I get 11.679.
11.679.
Yes, sir.
No. It can't be. It can be 11 point. Letu, what did you say? 79 point what?
79744.5.
79744.5. Oh man. Guys, redo this thing. All right, let me get a calculator. Because that's the ratio which I'm getting there, guys, something wrong. Unless if I'm paranoid 2 times.
Sorry, sir, I made a mistake.
Right, 12 times 180 cubed. 12 times 180. Remember I told you not to square. It might be a problem there, divided by 12 plus the other value is 264 times 9 cubed over 12. That one was 246, sorry. 246 times 9 to the power 3, right, divided by 12. Right. So if we do this more, let's look at the engineering. 11.679 times 10 to the power 6. So that's where the issue is. 11.679. Right. 11.679 times 10 to the power 6. So let's go and correct the radius of gyration, this one. 11.679. But the area, I don't think it's a problem. So let's correct that and see what's the correct value. Give us the correct value now.
So I get 19.707.
19.707.
707.
19. Is everyone getting 19.707?
So I'm getting 42.277.
Guys, you need to practice how to use calculators. I'm seeing calculator is a big issue. Can we create a course for how to use a calculator? 11.679 times
So I see where I went wrong. I didn't times 10 to the power 6. I just said to the power 6.
it's times 10 to the power 6 divided by 6,543. Right now it's making sense now. 42.249.
So shouldn't be 277.
No. 11.679 times 10 to the power 3 divided by 6,543. Oh, okay, you are right, because here I made it 4.3 instead of 3.4. 3.4, which is 42.278. 42.278 millimeters. Right. So from here, let's now go here and make these changes. It's 42.278, like this. Let's calculate our slenderness ratio now. What answer do you get? Maybe it's going to be in the hundreds.
So it's 109.986.
Which is equal to 110, right? So that's our slenderness ratio. So with this slenderness ratio, the correct slenderness ratio of 110, with this correct slenderness ratio of 110, we then go to table 17. So let's go to table 17. So if you go to table 17 for that slenderness ratio of 110, what is the allowable stress? So you go to the 110 value, 110 is 0. I'm going to get a PC of 69 megapascals. Are we all getting 69?
Yes, sir.
Right, 69.
Yes, so
Yes.
can you just quickly explain when you use the +0, +1, +2?
Oh, okay. Come in. Come in. What's up?
I did 3. It's like 2 teams groups. I did 3.
3.
Is it 5?
I'll put grid on the other ones because they say a minimum of 5.
Or minimum of 5. I thought it
Saying-
was 10%.
They say 10%, but not less than 5.
Okay, I'll do 2 more.
Okay, sure. Thanks.
All right.
Sorry, you're now under pressure. Right. Okay. So you've got L over R. L over R, that's your slenderness ratio. 0 plus 1 plus 2, then plus 9, right? Then going down, you have 0, 10, 20, 30, 40. It continues, right? Then in between, you've got values there. Right. So if I want a slenderness ratio of 25, right? So this is plus 2, 3, 4, 5, 6. Maybe this one is a 7.
Okay.
So if I want a slenderness ratio of 25, I go to 20 and 5. Where these two meet, that's the value of allowable stress for a 25 slenderness ratio. It's 20 units down, 5 units to the right. So if I want a slenderness ratio of 41, I go to 40, then plus 1. So this is the value which I then get. So that's how you use that table. Straightforward. You don't even need to stress and do all those things. All right. So for our case, we went to 110. So 110 and 0, right? That's your 110, which is giving us a stress of 69 megapascals. So that's how we got this 69 megapascals. Are you covered now?
Yes, sir. Thanks, sir.
Okay. So with this 69 megapascals, we can then say determine the maximum axial force. Right. So the maximum axial total force. Determine the total load. Determine the maximum total load. Right. So the load is P. P is equal to stress times area. Right. Let me write that. Stress times area. Right. So stress times area, which is PC multiplied by the area. That area is the area which we've calculated. So PC is that 69 megapascals multiplied by the area in square millimeters. What did we get as the area? In square millimeters, we got an area of how much? We got an area of 6534. 6534. And what answer do we get?
So 450.846 times 10 to the power of 3.
450.
0.846
846
times 10 to the power of 3.
which is kilonewtons. So the maximum force which you can place on that thing, right? But this force includes the self-weight of the column. It's including the self-weight of the column. So we need to subtract the self-weight from this 450 so that we see the maximum applied load, P. Right. So determine dead load. Determine self-weight. Of column. So the self-weight of column, we can call it GK, and that GK will be equal to the density of steel multiplied by acceleration due to gravity multiplied by the area multiplied by the length divided by 1,000, so that we get the answer in kilonewtons. Right. So the density of steel, we usually use 7,850, right, kilograms per cubic meter. But if a question specifies or gives you a value for density, you use the given value. Don't just use 7850 blindly. That is, if the question gives you, if the question gives you a value, then use that value. If the question does not give you a value for the density of steel, then use this value of 7850. So this is going to be 7850 times 9.81 multiplied by the area. What did we get as the area of steel? The area is 6534. 6534 times 10 to the power minus 6, because I'm converting it to square meters. Then multiply by the length. What is the length of our beam? Sorry, the length of our column is a total of 4.65 meters. 4.65 meters. Then we divide everything by 1,000. And this is the value of GK.
So where do we get the density of steel in the textbook?
The density of steel, you are not given directly. It's not there, but we can make use of the red book, Southern African Steel Construction Handbook, right? So the density of steel will be equal to 7 I'm going to look for the table. Let me just look for the table from the big red book or the clause reference which governs what is the value there. Alright, so let me just look for
So it's on page 2.10.
2.10.
For 2.4, other properties of structural steel.
Right, so you just go close 2.4, density 7850. So you just write Southern African Steel Construction Handbook, close 2.4. That's where we're getting the density of steel at 7,850 kilograms per cubic meter. Right. So what answer do we get here? What answer do we get?
So I'm getting 2.339.
2.33.
2.34, sorry.
2.34. Right, this is going to be kilonewtons. So that is the total self-weight, 2.34 kilonewtons. Right, so therefore, determine axial live load. You can say live load or imposed load. Right, let's just say P L. So PL will be equal to P minus GK, which is equal to 450.846 minus 2.34. Then you get the maximum load which can be carried there.
So I get 448.506.
448.506 kilonewtons. So that's the maximum force which you can put on that column, right? So that it doesn't buckle. If you apply more than this, then it's going to buckle. All right.